All right, so we're going to talk about what we've done in Module 1, and we can really think of this as descriptive statistics, or sometimes you'll hear it referred to as exploratory data analysis. Okay, hang on a minute, it takes a little while to write this. Data analysis. All right, that looks funny. All right, oh, analysis. That's why it looks funny. So anyhow, we're going to break everything down into categories and figure out what this all has to do. So our first categories are measures of central tendency. And I believe that we listed that on there, on our module as that. And these are things like the mean and the median and the mid-range. So that gives us an idea of what's in the center of the data. So you're saying, well, if I have a 25-point data set, big deal. Yeah, you're right, big deal. But what if somebody gives you a 25,000-piece data set? What are you going to do then? So the first thing you're going to do is run, in that case you would run some kind of a program to see the mean and median and such. So one of the things that you're going to see that we talk about a lot is the normal curve, or the bell curve. And that, of course, looks something like this. And its mean is actually a population mean called mu. And what you want to do is when you get that x bar, or the median, that's an estimate for the mean mu. So it gives you an idea of where that mean might be. All right, and the normal curve, as I mentioned, is a gold standard in statistics. And you're going to see how everything, well, most things that we do run off of that. All right, then the next thing we're going to look at are measures of variability . And those are things like the range, the variance, and the standard deviation. Sorry about the blue. Okay, and here again we're going to think about the normal curve. When we talk about the normal, the information that you get is always going to be the mean and the standard deviation. In that case, the standard deviation is the population standard deviation. And its name is sigma deviation. Okay, which is the 6 laying on its side. All right, so we want to compare that, or at least get an estimate based on our sample standard deviation. And standard deviation we refer to as lowercase s. When I'm writing it on this, it's going to be script S. On the page, it will be lowercase s in regular print. And finally, we have another set. I'm just going to refer to these as measures of location. All right, so here's you're going to pick up your percentiles. Your z-scores. And your skewness. Okay, so the percentiles, they're pretty straightforward. Let me flip the page here. Essentially, when you think about percentile, when you take standardized tests, you get a raw score and you get a percentile. And essentially the percentile is saying, based on this raw score, you are in the 89th percentile or something like that. Okay, pretty straightforward. All right, then the next one is the z-score. And those are very nice. Those are typically used for comparison purposes. So let's just say for argument, Mr. X takes the SAT and Mr. Y takes the ACT. So I want to see which one is going to go to my college. Let's say I'm on the admissions committee. So I'm going to say, all right, Mr. X's z-score is going to be X minus the mean of the SATs over the sigma, excuse me, my fault, the S over the SATs, and I'll get a score. And then Mr. Y, I'm going to have his score minus the mean of the ACTs all over the standard deviation of the ACTs, and I'll generate a z-score based on that. So I will compare z-scores and see who's higher up the chart. And typically z-scores, I think I mentioned this, run from -3 to 3. Now for skewness, skewness is very interesting. All right, let's go back to the gold standard, the normal curve. Okay, and on the normal curve, the measure of skewness is 0. So you're saying why? Well, when you've got a data set that follows the normal distribution, its mean is equal to its median. Okay, pretty cool. So, and we're going to run everything. When I get my measure of skewness, I'm comparing it against the normal, the standard normal, or excuse me, the normal curve itself. So let's look at the formula. If everything runs on the bell curve, then I'm going to have the mean minus the median over S, so my standard deviation. But if they're equal to each other, I'm going to have 3 times 0 over whatever S happens to be, and that just gives me 0. Okay? So we're running everything off of that. In the ideal world, if your data set follows a normal distribution, your measure of skewness will be 0. Well, guess what? We're not in the ideal world. So let's look at a couple of examples. Suppose I have a data set, when I plot it, it looks like this. Okay, so in this one we notice the bump is on the left-hand side. It's not in the middle. So this is what we call right skewed. It's actually the opposite of where the bump is. And the measure of skewness, if I were to calculate that, would be positive. When it's right skewed, it will be positive. Now another situation, suppose I have a data set and I plot it, and this time the bump is on the right. So we say that this is left skewed. Okay. Whoops. And its measure of skewness, if I were to plot that, would be less than 0 or negative. Okay? So this gives you an idea of how your data is shaped as opposed to the normal curve. Okay? And one more thing, talk about intervals. All right. So here again, yet again, my intervals run in comparison to the normal curve. So we have something called the empirical rule. And we say, if I set up an interval, x bar plus or minus 1s, and my data follows the normal curve, the bell curve, then I would expect about 68% of the data to fall into that interval. Okay? Similarly, if I have x bar plus or minus 2s, then I would expect about 95.4% of the data to fall into that interval. And finally, if I have x bar plus or minus 3s, I expect almost everything to fall in there, something like 99.97%. Now that's if the data, again, if we live in the in the ideal world, that's what would happen. And you'll see as we go on, as we get into our study, the normal curve, you will see where these numbers come from. But right now, consider them as given. Okay? So what we're doing when we do our intervals is saying, all right, how does this compare to the normal curve? Now, don't get choked up if it doesn't match these. That tells you that the data is not following the normal curve. That's all it means. Okay? Great.